And you are live.
Okay. Cool. Hello, everyone. Welcome to my space talk about the UKSEDS Lunar Rover competition. Just to introduce myself, my name is Easdown. I'm the current chair of UKSEDS for this year. So I got elected to the position this March, and my tenure runs until the start of March next year. So UKSEDS is the National Student Space Society in the UK. We run events all up and down the country, trying to cater to as many students as we can, really. So we run outreach events for the younger generations as well as our National Student Space Conference every March, and other events such as our Diversity in Space Careers Conference, and competitions like the Lunar Rover competition that I'll be talking about today, and the National Rocketry competition, as well as a satellite design competition in association with SSPI. So today, though, I'll be focusing on the Lunar Rover competition. This is something we've run for the last couple of years. So the first one was kicked off in October 2016. And then this year's competition ran through to July this year. So at the bottom of my screen there, you can see the websites and Twitter handles for UKSEDS, Bath Space Soc, because I'll be talking about the competition from the perspective of one of the competitors this year, Team Bath Roving, which is the rover team from Bath Space Soc, and then there's my Twitter handle and website as well, if you're interested. So let's get started. So as I mentioned, this is a competition that's run by UKSEDS, National Student Space Society, and the idea is to simulate the lunar mission that was in a European Space Agency design study from 2010. So this involves driving a few meters from a lander, about 15 meters in a straight line, collecting a sample of dry ice and sand, which is simulating the water ice that can be found at the lunar South Pole, and then taking this sample back to the lander for further analysis. So some of the core requirements for the mission were for the rover to be no more than 30 centimeters on a side, and for it to weigh or have a mass of no more than 5 kilos. Now, one of the key things with this competition that UKSEDS wants is for it to get students involved with how industry does things. So the documentation for the competition follows a format very similar to that of industry. So the competition kicks off in October each year and runs through until July. In December, the teams submit a preliminary design review, or PDR, and then in March they put in a critical design review, or CDR. Then after the CDR, they get some feedback on a review item discrepancy, or RID sheet, and the feedback comes from reviewers from across the space industry, and you can see some of the companies here that have contributed reviewers. So Open Cosmos, Rouse Space, and Thales Linear Space. The final test day of the competition is also held at Rouse Space, so we're very grateful for their help with allowing us to use their facilities. So the preliminary design review is the first document. That's the one that outlines the team's initial concept, describes who all the team members are, and outlines an initial kind of plan and budget and that sort of thing, all the kind of project management sides of the project. Then the critical design review, that's the one that goes in March, goes into significantly more detail on the kind of technical side of the rover. So this will define as far as possible all the parts that will be used. Describes a test plan, so how the rover subsystems will be tested, and then how the overall rover will be tested to ensure that it all works together. And so yeah, the critical design review is the more complete document, from which somebody else could probably build the rover. The RID sheet includes useful information about sort of where we went wrong in the CDR. So that's it's a standard format, so it's a good way of getting the information across. Now, of course, this rover, well, unfortunately, is not actually going to the moon, but it's a good proof of concept for that. So to make sure it is a good proof of concept, we still have to design for a suitable environment. So in our case, this picture shows the test yard at Rail Space. So we needed to be able to traverse the large slope in the middle there, which is about a 30-degree slope. We wanted ground clearance of at least 5 centimeters to make sure we could clamber over the smaller rocks and boulders in the environment. And we also wanted to survive 3G vibrations during launch. Now, this was simulated by a vibration test at Rail Space on their shaker table, which was a really good opportunity to subject the rover to vibrations similar to the actual launch environment. And it's not something you really get to do very often as a student, so that was a really valuable experience. Now, once we'd completed all the documentation, it came to the build phase of the project. So I was the team leader for Bath's SpaceOx team, and you can see here some of the steps we went through to build our rover. So we had a variety of people working on our team, from first years at the university right up to final year, and a variety of subjects too. So I'm studying mechanical and electrical engineering. We also had people just doing mechanical and just doing electrical. And I think we had 1 or 2 mathematicians as well who were helping out with the programming of the robot. So it's quite a diverse team, and it's always good to have that variety of perspectives on your team as well, so you can have a selection of ideas on how to design the systems and how to put them together, and also a range of experience, because it just unlocks more capability for the rover. So, for instance, with programming, we knew that we had people on our team with experience in programming, so that meant we could explore a custom control system as one of our options, and that is something we did end up going with as well. So the picture on the left here shows the perspex sheet that the wheels were cut from. So the wheels of our robot were laser cut on the laser cutters at the university in the mechanical engineering department, and we're very grateful to MechEng again for letting us use their equipment. So the design of the wheels had 6 of these pieces per wheel. So they were stacked together, well, bolted together, and then bolted to a sort of hub piece that was made of aluminium, and the hub was then held onto the motor shaft with a grub screw. So these wheels also, the wheel pieces also had their the spikes in slightly different positions. So that meant that when the 6 pieces for each wheel were put together, they actually formed a nice V-shaped tread on the wheel, which just helped with mobility that little bit more. So these wheels were a significant upgrade on the previous year. So in the first year of the competition, we also competed, and for that year we had 3D printed wheels. It was a reasonable idea in terms of manufacturability, but we discovered on the day that that we hadn't designed the kind of structure of the wheels very well. So between the axle of the wheel and where it joined up to all the spokes, there was a weak point in the design, and the small amount of infill on the 3D printing settings meant that that point just wasn't strong enough. So we ended up with our wheels breaking during the test day. So obviously that was not good. So this year we knew that we needed to have a complete redesign of the wheels, really. So the Perspex laser cut wheels offered a good solution, because you've got a nice solid structure there, and having 4 bolts attaching it to the hub meant that it wasn't going to come off the hub either. And then the grub screws worked perfectly the first time round, so we thought they'd be a pretty good solution. So we just kept with grub screws as our method of attaching the wheels to the motors. So in the second picture there, you can see the bottom half of our chassis. So that has the 4 motors that are bolted to the inside of the chassis, and that chassis box is an ABS plastic junction box that we bought off Amazon. And it's also the same shape and same design as the box we used in the first year of the competition. and that's something that would prove quite useful later on. So mounting the motors was a relatively easy process. We also cut the holes for the bolts for the motors on the laser cutter again, so that was another that was a good way of kind of making sure they're in exactly the right places. And then mounting the motors itself was pretty easy. We just had to put them into place. So then the third picture shows one of our team using the milling machine at the university, or one of the milling machines in the mechanical engineering department. So we had a selection of manufacturing processes. So a good amount of laser cutting, as I've already alluded to, but also some mechanical building processes like using the milling machine. So it's a good way of getting some really hands-on experience of using these kinds of tools. And it's something that we do a little bit of on our courses at the university, but it was good to be able to apply that knowledge onto a really interesting and engaging project. So yeah, there's one of our team using the milling machine to cut some holes in the roof of the chassis. On the right there, you can see a wider shot of one of the rooms in mechanical engineering and all of our equipment laid out for our work. So just to the right of the picture, you can see the bottom of the chassis and also a box section of aluminium. So this was used to attach the bottom of the chassis to the vibration table when we had the vibration tests. So then after the PDR in December, CDR in March, and then all of the RID sheet and the build process, it was finally time for the test day. So the build process had been relatively rushed due to exams, and we weren't sure about the funding of our rover, but we did manage to get everything built and assembled in time for the final competition day, which was on July the 1st, 2018. So here you can see a selection of photos from during the day. So in the top left, you can see our rover trundling over the moon yard, and it's approaching the sort of sampling site that you can see in the top right of that photo. So the sample material for this year's competition was well, and for the previous years was dry ice, but this year the sand that we picked up also counted towards the points. So the sample was scored based on how much mass we picked up, so it was just a simple matter of mass to points. So we wanted to collect as much sample as we could, really. On the top right there, you can see another photo of the rover approaching the test yard, and you can get a good sense of the size of the rover relative to the rocks that were around it. So some of these rocks were fairly large, and it meant we needed to have good real-time control of the rover so we didn't drive into any excessively large rocks. In fact, in that top left photo, you can see our wheels did offer a good amount of traction for clambering over some of the smaller rocks. But in that top right photo, just to the side of the rover, you can see a pretty large rock, which we certainly wouldn't have wanted to drive into. In the bottom left there, you can see a sample site, which was marked out with some flags. Our sampling system used a 3D printed arm, which was driven directly by a servo, and the servo was held onto the top of our chassis by some handmade aluminium brackets that were just made from offcuts of aluminium. The sample, when it was collected, was stored in a hopper that you can see just behind the sampler arm, and that hopper had been sized to make sure it had enough volume to store the maximum amount of sample. And we chose that maximum amount of sample based on the kind of 500 gram limit for the points. So maximum sampling points would be achieved by collecting 500 grams of sample. So we sized our hopper appropriately for that. In that bottom left photo, just to the left of the sampler arm, you can also see a small hole. That was a camera. So our robot was controlled by a Raspberry Pi computer, and it had a Raspberry Pi camera module on board as well. The idea of this was that we would drive the rover in a sort of first-person view, and we could have live video and steer the rover just based on the camera if we didn't have line of sight. In the end, though, this wasn't something we needed, because the sort of environment of the test yard meant that we had line of sight for the whole duration of the mission. So, but the camera was there as a good backup system anyway. So the sampling was relatively successful. We did manage to collect some dry ice and sand. Unfortunately, in our control system, there was a fairly significant latency. So I mentioned the importance of real-time control, and this is a challenge we faced. So the control system was also rather unintuitive on our controller. We were using an Xbox 360 controller. So the controller was connected to a laptop, and then the laptop was then connected via a Wi-Fi hotspot to the Raspberry Pi. The sticks on the controller, though, were kind of the wrong way round. So, for instance, to move the rover forward, you'd have to press back on the controller. This is something we can easily fix for next year, but just how quickly we had to develop the code, it was just something that ended up getting a bit messed up. But the bigger issue, though, was that latency. So our rover driver quickly learned which way round the controls were, but he had to continuously fight the latency, which was probably around 2 seconds. This does actually accidentally provide a fairly realistic time delay, as if we were on the moon, but it's not something we were wishing to simulate in this proof of concept design. So the difficulty with the latency particularly became apparent during the sampling process. So when we were trying to pick up some sample, we would lower the arm, as you can see in the bottom left picture there, and then would try to drive the rover forward a bit to collect some sample in the bottom of the arm before we then raise the arm to tip the sample into the hopper. The difficulty, though, was that the latency meant that when we had the arm down, we kept driving against it too much or lowering the arm too much, and it was just putting too much force on the arm, essentially. This meant that ultimately the arm snapped. So the arm was made of 2 pieces because a single piece would have been too large to fit on the 3D printers that were available at the university, and the arm just snapped at the join between the 2 pieces. So that was quite unfortunate, but we did still manage to get I think around 20 grams of sample before the arm snapped. So we did have some to bring back to the lander site. In the bottom right of the frame there, you can see our rover mounted on the shaker table at Rouse Space. So this shaker table is one that's used for satellites weighing sort of several hundred kilos or a couple of tons. So it's a powerful shaker table and a real piece of industry equipment. So you can see our box section there, the aluminium box section, which was bolted to the rover with M6 bolts, and the shaker table with M3 bolts, as per the specification that was provided to us by Rouse Space. So the vibration test was, well, there were a range of tests that were carried out. So there were random tests, a high sine test, and then another random test at a higher amplitude than before. So the random test, the point of that is to find all the resonances in the system. So we kind of learned that the wheels in sampler were the more vulnerable areas, probably. Then the high sine test is the one that actually kind of simulates the launch itself. So I think we went up to about 3G this time, or maybe 4. So it was a reasonably strong shaking. And that was where things really, well, quite literally started to fall apart. So one problem we had with this year's design, or during the test day, is that the wheel, the hubs used on the wheels had a strange size of Allen key that was required for them. So on the day, we just ended up with not having the right size of Allen key, so we couldn't actually attach our wheels very firmly. We ended up trying to glue them on, but it wasn't the most secure. We actually discovered this during the test run. We managed to complete the run successfully, but just after we crossed the finish line, one of our wheels came off. So the timing was quite fortuitous. But anyway, when we came to the vibration test, the wheel issues came back, and we did lose, I think, 3 of the wheels. One of them was really solidly stuck on and is still stuck on there now. But yeah, the other 3 wheels came off during the violent shaking of the high sign test. Another thing we discovered is that the box section led to a quite strong resonance in our system. So this meant that as it hit the resonant frequency, the whole chassis of the Rover started to pitch up and down quite strongly as well. So this is something we had been warned about, and we tried to simulate it, but it's quite difficult to simulate the whole system. And there wasn't really much we could do on such a tight budget, because our whole Rover came to around £450, which is probably around 500 euros, or about say 600 or 650 US dollars. So the kind of space rated interface systems that are used on spacecraft are significantly more expensive, so we knew we didn't have the budget for something like that. But anyway, apart from the wheels, the Rover did survive the vibration test. So we did lose some points for the wheels falling off, but we did manage to get some points as well. So we were quite pleased with that. Now, I mentioned earlier that during the test, or during the build phase, we used a chassis that was the same design as the first year of the competition. So the way that this came in useful was that we discovered on the morning of the test day that 3 of the 4 motors for this year's Rover, for some reason, weren't working. This is kind of a symptom of the short amount of time we had for testing, because we would have liked to have tested all the motors, and we should have tested all the motors individually, and that could have given us enough time to buy replacements. What we did instead, though, is one of our team had the very good idea of swapping last year's bottom half of the chassis with this year's. So effectively, because we didn't, so on the test day, we didn't want to have to drill a whole load of new holes to mount the motors from last year. So what we did instead was just swap the whole bottom of the chassis. We had to take out all the control electronics from last year and replace them with this year's, but it meant that we could use this year's control electronics with last year's motors, so that we had a Rover that would actually could actually drive along. So that was a very good kind of engineering decision on the day from one of our team members. So what was the final result of the competition this year then? Now you can see on the right there that we came 2nd overall. It was a result we were very pleased with. There were, I think, 10 teams attending the final test day. So 2nd place was a very good result, we thought. Imperial, congratulations to them. They did very well in the whole competition, really. They survived the vibration test entirely, made it to and from the sort of landing site during the run, and managed to pick up a decent amount of sample as well. So yeah, well done to them. And Manchester as well, they were similar to us, so they did have some difficulties during the vibration test, and unfortunately didn't manage to pick up any sample, but they did get to and from the sample site, so that was a good performance. But it was good to see the variety of Rovers generally, and I think all the teams learned a good amount from the process and the competition on the day as well. And on the left of the screen here, you can see our team on the day. We did have some more team members during the year, but unfortunately some of them couldn't make it to the final test day. But yeah, you can see our Rover there and kind of get a good sense of the size of it in front of the rail space sign next to its controller. And there's some of the team members that took part in the mission. So next year, so the competition will be resuming again very soon. For Bath, they will be making sampler and code improvements. So we're going to strengthen that sampler arm to make sure it doesn't snap again. And the code will be improved to reduce the latency issues we face this time around. However, the competition is going to be having a fairly big change. So it's going to become a Mars rover competition. So the competition rules are just being finalised at the moment, and the details will be announced very soon. But it's going to be a very interesting competition based on the latest kind of developments of rovers in the actual space industry. So we're trying to keep the competition as relevant to current activities as we can. We being UKSEDS, of course, and I'm on the committee which is deciding the rules for the next competition. Now, that does mean that I won't be taking part in the competition from the Bath perspective next time, which is kind of a shame, but it's also good to now be involved in the rule development process to make the competition as good as I can and as good as we can for all the teams that are taking part, and make sure it's a really worthwhile experience for all of our students up and down the country. We have around, UKSEDS has around 400 members, and with, I think, 10 teams making it to the final test day this year, we had around 60 or 70 teams on the final, 60 or 70 team members on the final day. So it's a competition that's really engaged a good proportion of our members, and hopefully we can get even more teams competing next year. So that's everything from my presentation, but I'd welcome some questions. So if you do have any questions, just stick them in the chat for this YouTube broadcast, and I'll be happy to answer them as they appear. Thank you very much. Okay, so we've had a question from Nitish asking, what were the primary requirements you had in mind for the project as such? So the main requirements for the competition were the sort of driving requirements were for the rover to be no more than 30 centimeters on a side, so no more than 30 centimeters long, wide or tall, and no more than 5 kilos. One of the other key requirements, though, was to have enough capacity for that 500 grams of sample that would score us the maximum number of points. But we also, of course, needed to get to the sampling site in the first place. So driving up the 30-degree slope was one of the really key requirements. So we needed to make sure that our motors had enough torque and the wheels enough traction to really dig into the surface and get enough traction over the surface to drive us up that slope. During that, when we were kind of designing our rover based on that requirement, we were assuming a worst case scenario. So we assumed that we had a rover with a maximum mass of 5 kilos and that we also had 500 grams of sample on board. So we made sure we had motors that could drive a 5.5 kilo rover with payload up the 30-degree slope with a good amount of margin. So during the whole design process, it's key to have enough margin in there to make sure that if any parts underperform, you're still going to meet the mission requirements. So they were the really main requirements for our rover. Thanks for the question. Nitish also asks, I take it that you had a differential steering mechanism for the rover. So the way we did it, we had the wheels on each side operating at the same speed. So we had one motor controller for each pair of motors. So the two motor controllers were Thunderbolt motor controllers that were connected directly to the Raspberry Pi computer that was receiving the commands. So there was one Thunderbolt for the left two motors and one for the right two. That made sure that they stayed at effectively pretty much the same speed. And yeah, you could describe that as differential steering or skid steering, I think would be a better way of phrasing it. So yeah, it operated like a tank. So we could drive straight forwards and straight backwards, or kind of do gentle turns, or turn on the spot if we needed to. So it was quite a versatile and flexible sort of propulsion system. So Jay asks, what was the power source for the rover, and would it be possible to integrate solar panels for this rover design? So the power source was a lithium polymer battery with a capacity of 5 amp hours. The capacity was more than we needed, really, but as I alluded to earlier, it's good to have a decent amount of margin. And we knew that even with that battery that was much bigger than we needed, it wasn't the mass wasn't going to hit the limit. So we thought it was good to have a good bit of capacity. So that was the main power source for the rover. In terms of integrating solar panels, it's probably possible, but I think for this duration of mission, it wouldn't really be that useful, because the test run itself, so going from the lander point to the sample site, picking up the sample and then driving back again, took probably about 10 or 15 minutes. And you just wouldn't really charge the batteries very much in that time, especially if it was a cloudy day as well. And so essentially we just made sure that the battery had a big enough capacity to have loads and loads of margin, so that we knew that we could drive for way longer than we needed to. So Nitish asks, is the material aluminium? So the wheels themselves are Perspex, so plastic. They were mounted to aluminium hubs, and then those hubs were attached to the motors by grub screws. And then the box itself for the rover was ABS, so another type of plastic. So generally, aluminium is it's heavier than plastic often, and also would have been more difficult to manufacture, because it's just a lot more kind of milling processes if you do it from scratch. And if you bought a box that was aluminium, it would be much more expensive than a plastic one. So to reduce cost and make the manufacturing of the rover easier, we used quite a lot of plastic components throughout the design. So Nitish asks, maneuvering the rover on a slopey terrain using the skid steering must have been difficult. What was your tolerance angle in terms of traversing on a slopey terrain? So we didn't actually drive up the really steep slope on the day. There were a couple of different routes you could take. So it was basically go up the slope that was relatively that was steep but relatively kind of clear of rocks, or you could go through what the organisers termed the Valley of Death, which was a little bit of a dip in the terrain, but had quite a few rocks and of various sizes around the place. So in the end, we ended up going through the Valley of Death, which wasn't as bad as we thought. So the traction on our Rover and those motors with lots of torque meant that we could get through there quite happily. And the large size of the motors also meant it was capable of getting over some reasonably large rocks. I mean, you saw a picture earlier of it going over one. So it was interesting to compare that against some of the other rovers on the day, which used rocker bogie systems, which had 6 wheels. But due to the 30-centimeter length limit, they had to be quite small wheels, and that meant that they tended to struggle with some of the rocks in the terrain. So we thought that 4 larger wheels would be better, even if we didn't have suspension. But yeah, so the manoeuvring wasn't too difficult, really. It was just kind of it was more the control issues than the kind of traction that made it difficult. In terms of like an actual angle for getting up a slope, I don't think we actually calculated it as such, and we certainly didn't test it, but we certainly designed the Rover to be able to accelerate up the 30-degree slope. So at least 30 degrees it should be able to handle. So if anyone has any other questions, feel free to stick them in the chat, and I'll be quite happy to answer them. So Nitish asks, did we use 3D printing anywhere? Yes, so the sampler arm was 3D printed, but this year that was the only 3D printed part. So that contrasts to last year, where we used 3D printing quite extensively. So last year the wheels were 3D printed, and also the bracket that held the servo onto the chassis, and the servo that would turn the arm. So the 3D printing in the first run of the competition, it turned out to be a bit of a weak point of the design, really, because those wheels with their infill issues snapped, and then also the servo bracket for the arm also failed when we were trying to drive the Rover forward with the arm down. In fact, that driving forward with the arm down was as part of a rescue attempt. So we had one of the wheels snap on the return trip back from the sample site, and I decided it was a good idea to put the arm down to act as almost like a tail, like a monkey holds their kind of stabilizes themselves with the tail, which was probably a reasonable idea, but I accidentally drove forwards kind of into the arm rather than backwards away from it. So that meant that the Rover just pushed against the arm and it snapped at the weak point, which turned out to be the bracket that was holding the servo to the chassis. So this year we avoided 3D printing where possible, really. And any more questions from anyone at all, just stick them in the chat if you do have a question. So Nitish suggests you could use helium balloons to simulate lunar gravity. Yeah, that's quite possible. You could do. For this competition, though, it wasn't really necessary because the rover is a proof of concept one rather than an engineering model. So it's not you don't need to take the environment into account in that much detail. It's more the traction and things that have a bigger effect. Although, of course, if you did use helium balloons, it would reduce the traction. So yeah, it's a trade-off. But there was certainly no expectation from UKSEDS as the organisers that we would simulate things in that much detail. But yeah, it's possible, certainly. Okay, so that seems to be everyone's questions answered. So, there's one question from Pradipta asking when this video will be available for replay. I believe it's available as soon as the broadcast ends. So, yeah, that should be quick. It seems like that's everyone's questions answered. So, thank you all very much for your time and for watching. And if you want to get involved with or see what UKSEDS is up to, you can follow us on Twitter at UKSEDS or on Facebook, just search for UKSEDS. If you want to find out more about Bath Space Sock, they're on Facebook and Twitter too, as is Team Bath Roving, which is Bath Space Sock's team for the UKSEDS Rover competitions. So thank you again very much for your time. I'm also on Twitter. It's at Easdown, WEASDOWN, and I'm at Easdown.com as well. So thank you for your time, and we'll end the broadcast here and see you on SEDS Earth and around the internet.